So, good morning. Welcome to the next lecture, lecture 4, in New Methods in Urban Simulation and Modeling. This one is called The Art of Procedural Modeling. So this will be about, in the first part, about abstract concepts, how to classify things in a way that a computer can understand it. So in a very applied example, things in urban design. So urban entities, buildings, and zonings, and so on. And what's the concept of a grammar and what's the concept of a pattern? This will be explained in the first part. And then, later on, I have the honor to show you some slides of recent developments where the chair of information architecture took part as well in urban planning and design. New computer-aided tools have been developed and presented, and therefore I will give you a broad overview of what is the concept now of street generation, automatically computer-based, and what are the processes for building generation, and so on. And even give you some examples from the practice, not just in urban design, but as well as in cinema and entertainment, as games and movies. So first we start with the design process. So what can we use for grammars actually? One idea of that is that most of the architects work with so-called evidence-based design ideas. So because we know it, we do that. Because we have learned it with our empirical knowledge, that this constellation will work well, and maybe we have evaluated this, we can do it once again when the next situation comes into play. And the idea with grammars is that exactly that kind of conditions where we see, for instance, here, that could be something more for Scandinavian parts. For instance, here we have a winter sunlight exposure to the front facade, for instance. If we have that as a kind of rule, that we have this is here kind of offset in front of the building and so on, and we can incorporate it as a rule, we could have it as a kind of building code, form-based code, or even as a zoning law, and incorporate this as a kind of example how the setback should be, that we get enough sun exposure in the front of our building, or our building front facade. Another development, what had been pursued the last years, actually only the last 20 years, is so-called performative urban design, where different kind of tools have been used to classify certain kind of densities that could from statistics, population densities, expected ones, projected ones, or really existing ones at the moment, that can be then translated into a code. That means what are basically the building heights allowed, is it already overachieved, or maybe it should be deregulated in that area. And another thing is that we can as well classify the optimal sunlight envelopes per parcel lot. So what you can see here in this white triangles, for instance, are the so-called optimal sunlight envelopes according to the parcel ratio here from the sides and so on for that area here in Brazil. And these buildings are actually much too high, as you see here, so it should be much flatter. Another example is, for instance, which is what had been used quite common in urban design, are space syntax methods to show the accessibility of certain kind of streets. So for instance, if you select this one here as the main street, here you see the analysis output for all the accessibility, where you can go within a certain time frame, maybe 5-10 minutes. I'm not sure for this one. And you can see how how good all the streets are connected to this point. For instance, if this would be like a kind of Broadway, a retail area, for instance, you want to make sure that all of the areas of the cities are mostly well connected to that area, and that you can get out as a result with that kind of simulations. So even from here, if you know about that, especially about the building forms, you can encode this into a grammar, or the functional relations. Another thing is what you can encode into a grammar is all that kind of meta information. For instance, if you make a site survey as you did now, or are still doing, with the form-based codes as an analysis, you rate maybe the urban qualities of that areas. And if you find out what are the specific parameters inside your survey that you're doing, you can maybe make a connection between this metadata about urban well-being, for instance. Are the people happy around the squares? You can incorporate as well that inside the grammar and make a connection to that. Okay. The goal of the whole thing is that you gather as much information and put it into a container where you have that form-based codes or grammar as you want to call it, and you have certain knowledge put into that system. This is implicitly there. Sometimes explicitly, sometimes implicitly. And this is as well as about some parts what you have in mind as an urban designer when you're doing your traditional drawings and drafts on the computer. You have all that sorts connected. Why is the square looking like that? Because there's a good accessibility to public transport, or there's a good view access to a site or whatever in that direction. You can do that with that more implicitly and put this together. And at least communicate it with diagrams in the end for certain scenarios. This is the step what you're doing right now. You're collecting information about certain kind of size ratios, or how are things placed on a parcel lot, what different kind of typologies are existing, although that is not form-based and smart code. But this is similar what you are doing right now to find out all about these different configurations that you have. So, all for the different types. And then, with doing that, you have all the necessary information to translate it to so-called design grammars. As you see here, this looks like a very cluttered, unordered place. But it has very regular expressions how all these shapes are put together.
Could you step to the other side, please?
On the other side?
Linke Seite.
Muss aber da drücken. Besser?
Ist nicht mehr mit dem Touch?
Ja, doch, ja. So I have to go on this side, as said. Okay, so, and what I just called it, one possibility, one tool to do that are so-called grammars. Maybe everybody knows some grammar here in this room, I guess. Otherwise, we couldn't communicate. So we learned something about that in school. So basically, grammars are used to describe and alter strings. So what I'm saying is a string in a defined manner. So the result are sequences of symbols. So for instance, we have subject, object, and verb in a sentence that can represent, for instance, a human language or a specific human language like Deutsch, Swedish, or English. Or it can be, for instance, an HTML code. It could be like a C++ code or a Java code that can be interpreted by a computer. It could be HTML. Or it can be architectural shapes. So if you look at the old temple from the Greek, classical Greek ages, for instance, they have a grammar used to formulate all the parametrics of the temple, all the columns, and so on. And these specific grammars are called, because they are related to shapes, are called shape grammars. So as I said, they're actually a very nice answer to all the things that should be inside a computer-based model. You can store spatial configurations and metadata. So, I have to check where's the right one. I guess this one is the right one. So now we have a bit of theory here, how such a grammar is constructed. Actually, a practical implementation you see within City Engine in the script interface, the script interpreter. So the idea is that you have a so-called set of start symbols, here in a general mathematical way called N. The start symbol, for instance, is lot or street. So if you have worked through the tutorials and had been participating on the last tutorials in the class, is for instance lot. The very beginning is a so-called start symbol. And then we have a set of so-called terminal symbols that are disjoint from N, sigma. And these ones are all the things with the dot in the end. So it's like the closing mark, the last rule, like color A, or like texture, or like a terminal presented in the end, insertion of a column or window into the code. And then we have a so-called set of production rules. So these are basically the set of all rules that we have inside the City Engine grammar file, rule file. And the whole construction, so to say, the whole rule file represents the language. So it's a very specific language that you have created to formulate a specific design, or at least a design space. Since it's parametric, different possibilities can be interpreted or come out of this code, and therefore you could even say design space. And with this design, all these components, you can construct a string that can result into a building. If you go to the sequence from lot to all the things, to all these rules, you start with the start symbol, S, for instance, or lot, and then you apply all the rules that are stored in P, so all the rules that we have listed inside. Then you get the sequence. So, one example, we have given this, the start symbol S, and we have two terminals A and B, and we have two rules which are using these components and transforming those components. Then, for instance, the first rule could be S evolves into A, S, and B. And the second rule may be like S evolves into B and A. So what will be the major difference of the two rules? Anybody wants to answer?
One includes S.
Yeah. Okay. And what does this S?
Start.
Well, it's like a loop. It starts again.
Okay.
So each time the compiler sees that S appearing, it will start again. And if the distribution, the stochastics, for instance, if you have stochastics in play to trigger rule 1, then always that rule will be recalled forever. So for instance, if you go here, S, first rule, A is B, again first rule, you just insert in the middle. The next step is actually, like in City Engine, if you have the split done, you insert here again the next rule, have the next component, and if you then trigger on another one, like the the terminal rule, the finishing rule. So you could say this is like a repeating rule, this is like a terminating rule. Then the process actually stop and the string is completed. So this will be the resulting string. And for all these rules, the possibility of all the strings, so the design patterns, you could say so, is out of that set. This is then called language. Another example. Oh, there's something strange. No. Okay. There's something in the layout different. Okay, as expected. Okay. So these are the rules. And these are possible productions. Actually, it should be the other way around. Sorry. So for instance, if you just start with rule 2, you just get ABC, that's it, nothing more. Or if you go here like a sequence from 1, 2, and 3, and 4, 1, 2, 3, 4, we start, for instance, with ABSC. Then in the next step, what's here? S will be exchanged with ABC. Okay, so we have now AB, AB, C, C. In the third step, we have BA, like moved around, translated to AB. So we can use it as a kind of sorting. And then BB, the sequence BB, will be changed into BB. And then we have that ordered sequence AA, BB, CC. Interestingly, this whole construction set will always come into the result of a language like A high N, B high N, and C high N. For all that N's that are more than 1. So for whatever you do, you will always get a sequence like ABC, AA, BB, CC, or AAA, BBBB, CCCC, and so on. So if you think on facades, for instance, where you have repetitive elements, that's a very typical example. So now we make a little comparison to what is in CGA shape inside. CGA shape is as well a grammar interpreter, computer-generated architecture, grammar, the abbreviation for CGA. And the start symbol in that case is lot, street, corner, and so on. And the alphabet is actually representing all the variables and the inbuilt functions, what you have been using, for instance, built-in cube, and all the different kind of production rules. And the production rules themselves, they consist out of, the production rules should be out. Forget these rules there. And the rules contain the constants, the terminals, the variables, and the start symbol. And constants are like fixed values that are always used to have a predefined result, like deleting something or closing a string. So deleting something means that you can just, from a certain kind of scope, you can make holes. And to complete something is like the dot at the end of each sentence. And terminals, like insert all these constants here. Okay. Oh, that's funny. 8-bit was, okay. So what are the basic operations? So the basic operations that we have with CGA are transformation, scaling, and rotating. So T, S, and R. So are the very basic ones that you have. For instance, if you say, I want to have an A was the whole thing here. The boundary, the massing cube would be an A. And I want to have like 3 shapes coming out of it in the end. So this will be B, C, and D. And for instance, I want to have the B like a setback of 6. Then we have here like for X, for Y. In that case, Y is the upper axis. And Z, so Z is steps in that case. So Z goes like 6 steps back. And then we want to scale a cube out of 8 meters, 10 meters high, and 18 steps. So this will be like all that massing functions to set up the initial figure here. And we call it then B. So this will be the first step. And the next one is a branch. We have here like go to position 6 and do here a scaling, like 7 widths, 13 height, and 18 depths, and call it C. And as you see, here's even a kind of overlap in that area. And then, in the end, at the same position, so the position is not changed, it's on the same scope, so it's the same rule. Here, go 16 steps, meters beyond, and do a scaling for a bounding box. And then insert here, so this is an inbuilt function to insert like OBJs or different kind of existing files, and call it D. So, and then we have the basic composition of the Sternwarte of Semper in the ETH Zentrum. So, sorry. Is this clear how this works? Yes? Okay. So after we have seen the basic functions.
So just the first volume.
Yeah.
When do you build it actually?
Oh, sorry. This one?
Yes.
This is step.
And
so
what are you scaling there? Like 10, 18? It's just.
Yeah, we just assume that you have like inside this so-called scope. You always operate with so-called scopes, which are bounding boxes. And in the first scope, the bounding box A is like given on the existing space that you have. It can be the whole world. It could be like just a simple parcel lot. You just say, okay, partitionize the space into the 3 stripes, so to say, 2 stripes actually. The first stripe, second stripe. This and that one. And the first stripe, the first volume is here. You just say, I have like, maybe you know that turtles, logo turtles in computing classes in the first 2 years of elementary school. You know that. It's kind of simple. You have like a coordinate grid, and you just give some commands and say, oh, go to this position, like x2, y2, for instance, and it goes 2 up and 2 right and stops there. It's the same like here. We have here as well a turtle. Here's the coordinate system. It goes first here to that position. It's given by z. And at this position you say, okay, now you stop here. Now you do a scaling to make a volume at exactly that sizes that you have here. With this as a local coordinate system, what you have here. And then after doing that, you give it a name, call it B. So it could be like the first part of a building and so on, like a side wing. And then the next step, okay, now you go back to 0 here.
Yeah, that's okay, I was just asking because scale is a transformation and you need an object to make a transformation.
The object is already there. Yeah, the object was already there. It was implicitly there. It would, in this case, since it's not defined what an A actually is, it's the whole world space, so to say. Yeah. Okay, good. So, And if you have the spaces and you create those kind of volumes and subvolumes as subscope, so to say, you can split them. That's a very new idea, actually. And instead of having several distinct components and you want to put them together in a meaningful way, you have always a scope and go top down and put it in several subscopes. In that case, it's just on a plane, but it could be as well in 3D. And the idea here is that you can have a parametric design of cutting here at the ground floor level, introducing a prototype of a regular floor, and have a repetition to describe all this. So, for instance here, a facade starts here, the basic of a facade, and here as well, the scope given for the facade is the total height of the bounding box that is existing at this, where this rule comes into place. So for instance, this could be that large, it could be that large, doesn't matter. And then you say, okay, at 3.5 meter, you cut and you call it ground floor. So everything what is below the 3.5 meter is ground floor, for instance. And these are very generic variables. You just invent them. It's not something predefined. You can call it in anything. But it makes sense that you have a certain kind of convention for that. For instance, you want to increase something like a ledge. You want to implement this one as well. Insert this one. You just put it here, like 30 centimeters, a ledge. And then another symbol for splitting comes into play. And then you want to have floors. Not just one floor, you want to have several floors, depending automatically on the height given by the scope. And then you just say 3 double point floor, make a bracket, and a star. And the star is like, use this pattern and repeat this pattern. So use this pattern floor with diameter 3 meters in height and repeat it wherever. And you can see, of course, here's a little mistake. Who knows the mistake in this picture? What's wrong?
The roof.
Yeah, exactly. The roof is actually another rule. There's like a roof floor, just not put here. Okay. So, and actually, it doesn't matter how high your building is, the facade will be always looking, at least from the geometry like correctly. Okay. But to come at the facade and actually work with the facade, you have those volumes of your buildings or your floors, depending what you want to do. Sometimes it's good to work with volumes under the floor level, because then you have the proper reporting of each floor area what you have. And then you get the facades with the so-called component split. And this component split just reduces the three-dimensional space in two-dimensional spaces. So in that case, we have a mass model, and this mass model is split into faces. Therefore, comp and F. And all what's on side, just side here, is called facade. So these elements here all are called facade. So that seems to be very simple, but it's very crucial to understand later on why certain codes are working and why not. Morning. A lot of students sometimes forget to introduce at the very beginning already, like the component split, or maybe never do a component split, and then very funny constructions appear. So, and all those things that I just presented, the basic concepts of, can be put together, all these configurations, into design grammars to arrive at digital models that can be, for instance, prototypes. So this is the same basic structure as I showed you initially for Marrakesh Medina. This picture, what was like chaotic, and this is a a classification tool for all that kind of zoning patterns on a parcel lot. So for instance, this is an example from a colleague of mine, José Duarte from TU Lisbon. He had put on like the first geometric description of a basic zoning for Marrakesh Medina, and it's actually such a very generic that you can use it mostly anywhere else in the world. So it looks very strange with the colors, but has some meaning. So just imagine that these colors are representing certain kind of functions that are parametric, and it can be adjusted parametrically. For instance, this can be like a setback space. This can be like a green space. This could be actually the red one could be the building, and the yellow one could be the patio. And if you have the generic description for Marrakesh, you will find there are different kind of course, the green is a not green space in Marrakesh. You have different kind of configurations that come into play and are used in the end, but always referring to the very basic and generic pattern. So it's almost every time the same initial pattern that you have here. Also different use mixes and functions will vary, but the generic basic type is this one. And these ones are very, to really have a control or better understanding on this symptoms in urban fabrics is very important. For instance, in Marrakesh, if you go maybe like 40, 60 years ago backwards in time, there was, for instance, like a temperature of like, in mean temperatures between 27 to 35 on average during daytime through the whole year. And now, because they have this compact layout of all the buildings and with these narrow streets, everywhere there had been this AC cooling units to have cooler indoor climate. But what happened in the end after electrifying Marrakesh, everybody got these cooling units and put it there in place. And now all the temperatures are had been risen to a level like 35 to 42 degrees. So, and this is quite dramatic because even because instead of using indoor climate cooling, you still need to recool because outdoor is too hot. All these narrow streets and all these compositions are not made to get the hot air of all the climate cooling away. So therefore, we need that kind of understanding what is the existing principle, and with this existing principles, we can maybe find out what kind of solutions we can actually implement that make sense in a way that everybody understands it. You put it in simple regulations later on as a planner, so that even laymen can implement it kind of wisely and not making their life harder. So that's the digital model of the reconstruction of Medina. The focus was mainly on getting this graph structure of all the accesses done for different kind of purposes, accessibility studies and so on. So this was not City Engine, this was a different tool created at TU Lisbon. Okay. I showed this in the introductory lecture already. Another possibility to have these grammars is that we have very basic stereotypes configurations that we can use. And if we have those basic stereotype configurations, here for instance is the same theme with the Marrakesh classes that we have the setbacks, different kind of zonings inside. We can have already kind of tools that can help us to bring in certain kind of very simple layout studies for master planning already. Of course, as you see here, some of the shapes will never work, will never build so that kind in practice. But in generally, we have a pattern. We have a pattern which describes an urban fabric. And actually, this kind of pattern can be understood as a small grammar, it's a small language, specifically for a block, for just window types. Depends. how you want to describe it. So it has multiple scales, a pattern. It can be applied on a block, it can be applied on a facade, it can be applied on a zoning. And this grammar is a set of shape rules. So basically, if you're writing a rule inside City Engine, you're composing already a kind of pattern. It depends on you how generic this pattern structure is and how often you can reuse it with minor modifications, for instance, and to derive a certain kind of patterns that have a certain function. And since we have to describe the whole urban fabric, like buildings on a block, we have to describe streets, we arrive at an urban grammar that can be understood as a set of patterns. So it's all nested and linked. And the good thing is, where you come into play, everybody could have a different kind of answer to certain kind of things, as it is in real life. Urban designer A and urban designer B have a different interpretation of an answer to a given location. And therefore, we actually can have a set of different kind of designs into a pool of patterns. And this can be all done on different kind of levels. As I said, we can do it on the building level, patterns of 3D masses, or facade patterns, or we can do it on the cadastral level, where we have the lots with the footprints, where is the opening to the front, for instance, where are the open spaces, and how do they look like. And we can have it on a higher scale, like the street graphs, or the kind of blocks generation, subdivisions, and even up to the zoning. So it's all interconnected. It can be all set up as a parametric system, where each input feeds a whole beast, a whole machine. And even on each kind of scale, you can have different kind of pattern sums, so to say. All these different design answers from your designers. So for instance, it could be even like that for instance, P1, everything, the tree which is spanning out of P1 comes here, could be like zoning regulations, and P2 can be like a master plan, which has to be then to be compared with all that one. So this is all the abstract background to structure the project ideas. So just some old examples that we have here done in the past. So for the open spaces, or for Mazda, there was like we had the design task to find out about all the carvings that had been incorporated in the design rules of Foster and Partners, if they will actually follow the behavior for the flow ventilation models and sun exposure. Oh, sorry, that was one too much. Or we had, for instance, a zoning plan given for a district in, what was it? In Riyadh, yeah. For Riyadh was like 2 by 2 kilometers in size. And we had just the information from GIS, and a Foster and Partner wanted to make a quick layout. What will the city look like with all their kind of features that they wanted to have inside? Looks more like Dallas, but basically the idea was to have a first test. If you have all the different colors or different kind of land uses here, this is assigned to a rule base. You can just load in all the kind of GIS files, and then in the end you have a composition of a urban master plan, what you can look at and can say, no, that's maybe the wrong direction, maybe it's a very good direction. And further, we had used it for a project called Calcare, as well together with Foster and Partner, where the idea was to have, similar as in Mazda, very compact building shapes in the middle of the desert of Saudi Arabia. And this should be like a very energy efficient city. And not CO2 neutral like it is in Mazda, but energy efficiency. And we had as well like different kind, like so-called transects, that very simple transects here in that case. We had as well all the different kind of granularities of urban shapes, the basic shapes, and then we had made a prototypical study of all the generic compositions that could create some urban fabrics and spaces very compact and following the local schemes. So, and of course, was as well a highlight project, the reconstruction of Rome, where you have as well all the different kind of patterns that are all known by archaeologists, but they didn't really excavate these buildings. They are not existing. There are maybe some footprints of building walls, maybe somewhere besides the big temples. There's not much building fabric remaining, and all those different kind of patterns have been used to reconstruct Rome, how it was looking like in 300 after Jesus Christ. And of course, patterns are existing in all that kind of architectural shapes, like this very simple example, like the cruciform skyscraper of Corbusier, where you have those components, you have the wings, you have the core, you have inside this wing some examples of geometry, and then you just need little information actually to put this together into an architectural shape, and even have this different kind of variations here. And of course, the last step would be attaching facades to it. Yeah. Okay. So this is just quickly. There's a later lecture where we have this bit more in detail, covered in detail. So if you have all those kind of patterns and you even get this urban forms out of it, so it's like a first idea how you will work like at the end of the semester. You have the input from the GIS system, from Altstetten, for instance. You have the city engine. You have the rules, the rule base. You connect the data from the GIS system to the city engine. And you have a tool for evaluating the performance. This can be, for instance, ArcScene or 3D Spatial Analyst, or it can be Ecotect, for instance. And this will be all rendered in real time, then on a GPU at the so-called reality server. This was the one tool that I was showing you in the first lecture on the tables. And yes, so. Okay, so this was the first part of the lecture today, and now comes the second part. Do you have any questions so far, for now? Pieces that are remaining unclear or should have explained better? No? Okay, then we just go ahead. So the next thing will be to talk about urban layout and road network generation. So there is a huge process ongoing to automate a lot of urban design structures in the creation process. A thing which is really hard to model and to do are urban layouts and road networks. And I think for us as architects, it's very important to have at least a broad sense what is actually done in computer science, because they do it anyway, even without asking us what's our opinion on that kind of techniques. So at least we need to be aware of that, need to know about the benefits, and maybe as well have an idea on critique. So these are some lecture slides that I have from colleagues of mine. They did the so-called SEGRAPH course this year on urban modeling. And maybe you know SEGRAPH already. It's a big conference on computer graphics, mainly known for entertainment things and so on. and all the latest computation and animation tricks are shown there, all with computer graphics. So, and one of them, one kind of new stream is urban design and urban modeling, but really from the computer science point of view. So one of the ideas is what we are interested in as well is that they have tools that where you can model plausible road networks. So plausible means it looks really like it should be, and we have all the different kind of components inside, and therefore we go just through a short history of the different kind of approaches. Here we had so-called L systems, which is represented somehow in the city engine with the street generation algorithm that I have showed you in the first tutorials. Then we have so-called example-based modeling. So you have existing images and you compose out of these images like the different kind of layouts. And the same with example-based urban layouts, which is more working with the explicit knowledge inside the images and so on. Then a very interesting thing, which is very intuitive for architects, is tensor-based modeling, where you have so-called tensor fields. You know that still from physics, tensor fields? You know that? It's like these magnetic flow fields that you have. And just imagine you have flow fields where all the streets align to it. I will show it later on. And shortest path-based modeling. So it's especially important for sculpting 3D urban environments. And there you have the best passes along the surfaces, like roads put into place. And yeah, then we have all this layer-based typology preserving and changing transformations. It's like this automated and parametric blocks design, what you have in City Engine. You can move streets along or just introduce new streets, and all the different kind of shapes will behave the same. So this is one of the very early City Engine pictures that are existing actually. It's had been done by my friend Pascal Müller in the latest 90s. He was doing that as a student actually here at ETH, studying computer science. He made some tests with all the different kind of shape generating procedures, L systems, and with all the generated layouts of streets here, he derived automatically a subdivision of Manhattan blocks. Actually, it's one of the most easiest forms that you can generate are this very rectangular Manhattan blocks, and then just extruded then somehow those shapes and textured it and rendered it those days in the Zentrum at the supercomputer which was there. And yeah, so he had Manhattan created at the Zurich Lake, yeah. And so how was this done? You had several inputs, like this case it's population density here, with this population density and the terrain elevation. You use the particle system to connect different kind of parts of the city to the center, which had the highest density in the end. Then the first system of highways had been generated, and then just further all the different kind of streets, and from there blocks and lots and building geometry. So yeah, as I said, so it was kind of amazing those days. Nobody had ever used a technique which came actually from botany. Actually, L systems had been used to describe plants, growth patterns, and to construct artificially plants. And this is just a comparison of the automatism and how it looks like with the real-world picture of Manhattan in that case. Of course, he could introduce a certain vector that the orientation of the layout is almost the same. But it was already very amazing. It was 11 years ago already, yeah. Yeah. So as well, one of the first attempts to have a street network, and then from the street network, you have attached predefined widths to the graphs. Then you have the setbacks, you created the blocks. And from the blocks, there was like a first attempt to make subdivisions. But as you see here, you're already kind of very small pieces, and you didn't really have control on that. So the next step was not just to subdivide everything, as well that you can have that kind of shapes, not just on the plane. You can use it as well to construct volumes. For instance, this volume can be replaced by that volume, and that volume can be replaced here above that with that volume, and so on and so on. And it was really not intuitive. It was really like a very extreme hack. I was using the first system myself with Antje Kunze. It was very funny actually to work with that in the beginning. And facades, for instance, was more like a placement of textures. There was not really a facade, was not much geometry. It was all about like you have a so-called sequence of frequency, maybe frequency is a better word, of different kind of things that happens inside your facade. And for each frequency, you could make in a set for a new rule of a frequency. And then in the end, finally, you had a facade texture what you could just paste into the last remaining pattern of this frequency. And this actually, as far as I know, it had been not implemented in the prototype of the city, and it was more implemented in a tool like Maya, for instance, to do that procedural, procedural textures to describe facades. But actually, as I said, the LSIM systems had been used to generate plans. And it was even farther explored to create ecosystems so that you not just had a single plant or even a very funny plant, or maybe like this one, a violet. It's violet? No. Flieder. And even whole ecosystems. So, which is now available in commercial tools, actually. This is the inventor of this system, Oliver Deussen, had been then created a software called XFrog, which maybe some of you know, but can be used as well to populate 3D environments with plants and even have growth scenarios over time. And it's kind of commonly used in some movies, and maybe another thing what is well known is Vue d'Esprit from Eon Technologies, where you have as well like plant systems and ecosystem systems for very natural placement of things. Okay, so this has been the first analogies, and then the first techniques. And then we come to image analogies. So maybe we don't want to really have this for urban modeling and composition. We don't want to have always the street networks and all that information. Maybe it's too low level. Maybe we want to have a first sketch. So what could be interesting? It would be interesting maybe to have maybe something at hand where we can learn how, if we use this technique to get from there to there, to a certain result, how we can use it again. For instance, for a totally different picture to arrive at as well like an aquarelle image in that case. So this is just the image processing. Has not much to do with urban planning right now, but okay. But somehow we have those two-stage design idea. So in the first phase, we have a pair of images. What we have, the one as the filtered one, the resulting, and the one is the training data. And then we can create a so-called analogous filtered result. So what does it mean? So for instance, if we have the same procedure applied to urban design, for instance, if you just want to modify a view on a city, maybe we could work like that. We have like in unfiltered source, it's actually like a Photoshop layer, you could say so, where you classify all this kind of building information, maybe in blue. So these are all built fabrics here. Just color it. Okay, then we classify, okay, all what is blue here in this picture, all what is like water, it's a bit strange, but is red here, for instance. Okay, so we have the land use or land occupation of waterways. Then we have something here in violet, and this violet things, this could be all different kind of ways and structures like that, or built fabrics, I don't know. And then we have all the background noise, which is like greenish stuff, which is still remaining in green. Okay, if this input data, we can, I think possibly we can already do it in Photoshop. We can repaint the whole scene if you want to redevelop. Of course, it's a very strange example here, but we can just introduce this one here, this blue, transfer to here, have it here. Now, and so on and so on. We can even modify the whole layout. So this would be a whole new way of sketching. Of course, the results, there will be some ugly parts inside, which are absolutely not looking true. But if you have a minor resolution and just a first view on it, it looks already like a perfect image of like something which had been really photographed from a plane. And by the way, there is a little joke. If you look here, the Pentagon was just rearranged. It's not any longer here. That image. Actually, strange picture. Okay. The same idea can be used as well in combination, not just with this pixel information, can be used as well with all the kind of vector information that we have. So just imagine we have a layer of a GIS-based structure, like all this kind of street network, and then we have all the different kind of pieces from a satellite imagery that can be just reduced through the information from the parcel lots to little texture tiles. And this information can be used to clone from here the information, what are the typical kind of points and vectors, how are they correlating, to fill in with a grow system like it was presented before by Müller. And then you have the parcellation, and then you try with the computer algorithm to find all the snippets that you have to place them most accurately into this layout. And very interestingly, you get a fabric that almost looks like a logical sequence starting from here going to there for automatic completion of the rest of the whole fabric. That's very interesting. Of course, it has has many wrongs inside. It just looks like an urban fabric. It's not really something what you can use for planning. But this is the first attempt where you just imagine if you have a potentially very nice urban design, or maybe you know this kind of urban constellations of this urban structure is working quite well. Maybe for initial composition and training, you can actually clone and reapply to a different area. So this is a new kind of working, and which raises a lot of discussions. But yeah, so yeah, this is the aerial view. The streets introduced, and then this is the filled layout where you see here. So they just kept in that floors. Of course, you can now smooth all the kind of street graphs, so it looks more not so artificial. But I guess they just kept it inside on purpose. So this is the observation data. And here you can try to simultaneously set it together, and yeah, you get from here, actually, as I said, you have the decomposition and then compose it again together to a new layout. Okay. You can just skip this. And you can even go to the detailed information to the building level. And then you have this new layout in the end. And you even, after having that information, you even have it with underlying background information about different kind of land uses. You can even go that far that you can say, okay, we can really have interactive reconfiguration of urban layouts. For instance, if I have all that blue is residential, then we have retail with red, and green is industrial, and we want to redevelop some parts that we have some more working potentials for employment in that areas. Maybe we can reintroduce that, and then it can be automatically reconfigured, just to have a sketch as a view on that. As you see, it's just coming from the computer science, where they are very intuitively just working on it. Yeah, they're not questioning if it will make some sense or it's good for urban design and planning. They're just using it. And of course, all the little tiles, it's not really usable but for really creating the first sketches, for having maybe interactive tools to get a direction of what a design can look like in the end. But you always have to keep it in mind. It's just an interpretation of how urban designers will work or should work or whatever, and what's possible. So, a lot of technical problems as well still included, like all the scaling issues of different kind of textures, putting it into new parcel lots and so on. So another thing which is very interesting is the tensor-based method. So for instance, a tensor field usually is something what you have in, if you have the magnetic fields of the Earth, for instance, between north and solar pole, you have all that fluctuating gray shade image of all the different kind of magnetic fields that should go from this corner to the other corner, to the one pole to the other pole. And just imagine we have a flow field around a city. It could be the input, could be like the elevation of the city. And then we have this different kind of elevated heights, for instance, which could be a very perfect input for placing street networks already, for different kind of reasons, of course. One is, of course, cost to build it along the same height is perfect. But the other one is that you can very intuitively form the streets along existing natural contexts. And it's a very nice way of editing. You just imagine, instead of changing little vertices here, you could actually paint the overruling structure of your street network. So, as I already said, this is very, very interesting. If you want to find out about new roads, major roads, but for all the little details, it's not so well usable, because there are usually not so much changes. But for greenfield planning, to create the first layout of a city, this is very interesting. For existing, I think it's very complicated. So these are some of examples of tensor fields and what you can receive from the input and what you can mimic with the tensor field here. And you even, that's kind of typical structures that you have here, can be then found certain relations in between, where you can then set in here the major initial compositions and vectors that can be used to generate the major and the minor streets. So, and it's always like you're at a certain point, you arrive at the street graph generation and then on the geometric generation. So, one example city once more. Okay, so this was about the tensor fields. I personally think this would be very interesting to have it combined with this painting techniques, all this touch-based computing for layouting. It would be very interesting. So another example for the procedure generation of roads is presented here, that we have the best path. The idea is that you have, if you have all the elevation issues on your topography, what will be the best path for a road to go along? That's actually a very interesting thing. Usually it's still more or less computed by hand, by cartographers right now, to find out the best ways. So we have different kind of ideas. It could be just a smoother path, where you go more comfortable through the environment, or it can be a sharper path, which may be a bit shorter, but maybe even as well very costly. And the idea is that you have some functions about the cost for the curvature. If it is something like a river, of course you can mimic a river as well, water depth, and the slope that you have here. So that way you can really say, okay, we have maybe for planning, we have certain kind of functions that we want to have the optimized path along that surface shape, or maybe we want to introduce automatically a bridge. And I think this kind of things are very interesting techniques actually to find out a bit more about qualities. So this could be used to, if you configure it rightly, to have on the one side you have all that kind of view angles that you will have with your transport method that you're using here, but as well like all these trade-off examples with the distance and so on, and how easy it is to be integrated into actually the environment here, that path is here. Oops. Yeah, and as you see, some very nice valleys have been used to have a, I don't know, I guess it's more like for a race, huh? to go here with a car. Or, no, with a bike, I guess more for a biker. Okay. Okay. So, that was the one thing. Then we have what is kind of more interesting, the idea of the interactive modeling of city layouts. Some of the things that I'm showing right now is already implemented in the current version of City Engine. So the idea is here basically, just assume you have set up a greenfield planning, or you have an existing layout, a certain area where you can plant something and change something, and you just have introduced a layout here for having your block. And somehow you want to move this block because, I don't know, because some distances you don't like right now and you want to exchange this one with that one. And just imagine you have a contextual scene where you just take this block here and move it here. So. And going there, that you want, for instance, have the idea is that moving a street could be that you don't actually have the street available. That actually the street is like another layer. You just put it on top, and you have the existing network is not touched in the first place. So the idea would be that you can just grab the street, bring it here, and all the rules that had been used to subdivide, describe the zoning and so on. Therefore, it's very important to know about the zoning laws, all the principles at this current place can be just put here and then re-subdivided. So this is actually already possible in City Engine right now. And basically, it comes into place that we have different kind of structures available. We just have different kind of classification of different kind of networks. And so we need to decompose those parts and take it away and retransition it. So maybe this one bit better. So for instance, this is the initial layout. Then we have like introduced like a highway or maybe a new tram, maybe it's a tram line, cutting through existing blocks, scary. And then you see through the overlaying process that you have here, all the different kind of subsections are made. So you need to just to keep this in mind, how these things are actually interconnected, since sometimes you're wondering why a system like in City Engine you're doing certain things and why doesn't it behave like that. But basically you can imagine that this of substructure is here included as a layering structure. Okay. So this is actually almost a revolutionary example how to Okay. Presentation effect. Okay. Which one is the right one? Okay, I guess that one. Okay. Yeah. Because actually before that was really hard to work with the street network. You just had the single kind of graphs and the single compositions. And now you have all the different kind of interactive parts what you can really change. So it's one of example of the early prototypes where you could do these things. Sometimes very funny layouts. Okay. So now we had talked about the construction of the street networks and the regional zoning and so on. And the next step would be to give you a broader understanding about building design. What is actually the latest trend? So you all know maybe Revit and Rhino, but maybe the next Rhino and the next Revit you can see right now here. So one of the very classics is procedural modeling of buildings, where the actual CGA shape grammar of City Engine had been introduced. So, of course, Beverly Hills is not state-of-the-art in architecture, but it has all the typical components what you have already on a lot and on a building. So it was already possible, like very initially, to do that. And one of the first ideas as well, the Semper Sternwarte was used for many experiments. As well that we have different kind of modifications and variations of an existing design. So for instance, with the model of the Semper Sternwarte, you could easily introduce new kind of stories, and you even could move transition the design between the Semper Sternwarte and the Villa Savoye of Le Corbusier. Was but a very scary example for most of the architects. Very ideal examples had been all those kind of temple shapes. So actually the first users of this modeling technique had been archaeologists. They just had excavated tiny fragments and portions and little information about the actual architectural shapes. And with this information, they set up like a rule catalog, how this shape should actually be compositioned together. And then with this grammar-based technique, like in City Engine, it was easily to complete the structures. For them, it's very important, since they just have the money paid for excavating sites, but more or less they don't have any money to actually to create models out of it, to create some sense in the context. Another thing was that it's a moment, as you know, it's all script-based. You have some visual interfaces, but it's still very limited. And since the last years, like 2008, have been always like the ideas that you have a more or less visual interface to change on your urban design, building design in that case. And yeah, there is no direct artistic tool where you can go into the facade, modify something, some ideas, and we have mostly something like text-based grammars. Of course, now it's a bit different, but here there was one idea for a solution, that you have direct control, very ugly building, but on the shapes, that you can access certain portions of your grammar, modify and change something, but it still looks very tashy. Another idea was that if you have those grammars, maybe one could use it to create automatically layouts. So it's the architect building into the computer, very funny. And as you see, the result is interesting. But seriously, there are some applications, for instance, in hotel planning or in airport planning. We have different kind of sequences of rooms that are put together that needs to be there, or like factory planning, where those things could be actually used. I mean, of course, the architect is not made unemployed here, but it's more about to have more, make sure that all the functions are actually in the end included. And as you see here, it's not very simple to arrive at a kind of very plausible 3D model of a nice US family home. We have a so-called graph of all interdependencies for each floor. Actually, this needs to be layered above one. How a layout needs to be organized in all the ways of the functions with the architectural program. And there, a set of floor plans are derived and then composed into a 3D model. So this is very, not really easy, actually. There are papers and attempts presented since the 90s to create that kind of layouts. Sometimes it's like a test from chip design, from computer chip design. They have similar problems. But of course, in architecture, we have so many implicit and tacit knowledge included that cannot be really expressed with that automatic models. But it's a very interesting approach if you have all different kind of functions inside a floor plan or even an urban plan. This can be used to set it up. So these are some of the examples, like total square footage, the footprint is connected, then have a kitchen, then we have a living room, we have a kitchen, maybe there's an adjacency between kitchen room and living room, and so on. So that's brought into a logical network. And then there is an optimization algorithm put into place to actually compute then the optimized final layout. And that's very interesting. That's are the parts that are coming up into the brain of the architect, and now the computer tries to mimic it, like snap walls together. So we have the simple compositions of all that graph network, or split into collinear walls, for instance, slice the entire wall, and all the different kind of functions. What you're doing with your pen very intuitively. So, and then of course with all the different kind of iterations for this metropolis algorithm, a better and better variation will be found. Interestingly, it's the same approach that you have if you have a rendering technique right now. You render an image which looks photorealistically. Usually the same algorithm is used. So, and now the scary part comes into place, that you can, for all that floor plans, it's like the idea is like with a web browser, only the content counts. So you have the content, like the text in the web page, but the formatting, so the architectural style can be exchanged very easily. So that's one of the ideas. So I guess all that kind of real estate developers, they're just screaming for some tools like that. Optimizing the costs for the floor plans automatically, not paying an architect, and then just applying a different style for different settlement. Yeah, okay. So I think architects shouldn't be afraid of that. But I think that kind of tools can maybe but help to, while you are in the process of designing, when you get different kind of ideas, maybe how to replace and reorganize things, this could be very interesting. So, yeah, almost at the end. Still awake, great. So, another idea is actually that you could interpret for reconstruction buildings. You could use like curvatures, like profiles for each parcel. Instead of having these volumes, you place the volumes and you cut it somewhere and you paste and place something. You could see everything is not a volume, it's maybe just a profile that you just go along at the corners. So this is the next idea that we have here. And for instance, we have certain kind of paths around the building, and this could be used to go along those corners and to create certain kind of shapes. This is a totally different modeling approach. And we can introduce as many kind of profile lines as we can do, and then we get different kind of results. And sometimes this makes a lot of sense for the reconstruction, also modeling of the roof lines. As you will see in City Engine, with this predefined roofs, it's not really easy to get actually a meaningful roof. And I know all the programmers' work that had been put into that thing that is already there, so it's not very easy actually. Yeah. And you can insert like springs and that come outside the building and so on. And here are different kind of examples what you can do with that kind of profiles here. Very nice cottage homes, huh? So I guess for something like Disney and Pixar, it's very interesting to have that kind of techniques to just produce geometry on the masses. You have very intuitively, you can just modify the major components of your designs. The next thing is deforming architecture. That's very interesting. And, oh, next slide is of course. So which one is the right one? Yeah. So just imagine you have a set of pieces and you can just go here and take it and stretch it and move it around. So to say, you just move those parts to the next step, and all that things will always follow like logical functions that you have, like these components are put together, the right constraints are met, and okay. Actually, there is something about structural design as well. So and then reshaping architecture. That's very interesting, actually. You see here, there's a little input image here on the side. This was the input for, I don't know, maybe it's in Singapore. I don't know. It looks very Singaporean. And then you just have this as the initial interpretation, and then you have all the possible variation made out of the system. So the idea is, for instance, you have this as an input with all the different kind of shapes and zonings, like setbacks and different facade structures, and then you create the bounding box hierarchy here. So it's all about the masses, about the different planes, and inside that one you have different kind of behaviors, how it should act actually, and then all those behaviors are graphically interconnected with paths. So that can be used if you now have some knowledge about these paths for for getting a kind of knowledge about what the architect would have had in mind, for instance. So it looks very interesting. Just imagine there's just a concatenation of different elements that are put with a kind of glue together, and if you stretch those glue, the next logical order will reappear. So now we have some more scary images. So this was the input. Maybe this was this tower here, I guess. And with that idea of having this graph interdependencies here, you can shift around everything, and you can have always that same design. So the design idea. So the same with this and with that one. So that's very interesting, I guess. The next thing up, this was what I actually wanted to show, is that you have structural sound models. So if you imagine all this kind of grammar-based techniques could be used as well to make like structural analysis. If you create an urban master plan, and for instance, if these areas in Japan are rebuilt, then maybe it's nice to have something at hand which can look at potentials for disasters like earthquakes and so on, or just for entertainment, in this case to crash down the monastery Cluny. And yeah, so the problem is usually that you have in the computer-based model, you usually have all the different kind of vertices and put together, but not really structural information. So this needs to be revised, that you have structural information instead of having the elastic material. You have basically masonry inside. And this needs to be considered when doing this stress analysis and how this whole model will hold or go down. So you have certain kind of forces applied to the model, and then in the order of the forces you will have a breakdown or still a consistent model. And of course you can use it as well for optimization of the model, since the values can be adjusted to certain kind of cost functions and so on. Or different kind of examples here. Okay. Another example is modeling of facades. A rather old academic work here, instant architecture. The idea was actually to collect patterns of designs for each set of facade shapes or facade pieces, building shapes, very early paper about that, and to have a kind of split grammar to get all this kind of double slide information here. So this was the introduction of split grammars. In those days, when just the first revision of City Engine arrived, was a very great breakthrough actually to go away from these L systems, to have more control about the design. With the split grammars that you have this defined scope, similar as in the L system, but you could have more control about all the different components that you have here, even placing special elements like a sign, whatever. And with that kind of split grammars, you can even do recursive modeling. In theory, you can have like make a photograph of an existing building, and you can define yourself the split lines, or you let the computer do that. There are some of examples as well. So there's some pieces that are redundant. So it's actually the same procedure as what I showed before. Then we have as well like the continuous model synthesis, as well a very interesting approach, where you have one given building shape, and from this building shape you have an interpretation of variations, and you just give this 3D dimensional building inside, and the computer automatically calculates different kind of setbacks and additions depending on the space requirements that you have here. So it's actually similar as in Photoshop, where you have this cloning of a texture and the reapplication on a different area, but now with 3D models. So the idea is basically that you have like this voxel cells, and all this kind of cells will be brought together in interrelation, and you can use this to reconfigure these buildings very easily. But this is really like not usable for I should end right now, huh? Is this the message? No. Yeah, so for instance, starting from here, you have this type of configuration, the initial configuration. Then you can use this configuration out of 4 pyramids. You can recreate a picture of having different aggregation of all the different pyramids together. This can be done if you have all these different setbacks out of a building mass and so on as well for this one. I mean, an application for this kind of things can be, for instance, where you want to have little data storage, where you need just very little information somewhere. And for instance, for a navigation device, where you have different kind of very simplistic styles for navigating through an urban environment, you can use this to automatically construct a 3D environment and have maybe better feedback for orientation. So one of this kind of buildings, and you get that results out of it. And I think for this very stereotypes for you can make out of an ugly building an ugly city very easily. Yeah, but this could be really used for this kind of purposes. It's like really meant for that. A very interesting example, but unfortunately I don't have any further information on that, is that you can use as well these procedural techniques for creating freeform architecture. One of those guys who is very much into that, actually in collaboration with, what was the professor of Anastasia, Antje? With Patrick Schumacher, for instance. This is Helmut Pottmann, a former in Vienna, TU Vienna, mathematician professor, and now working in KAUST, Saudi Arabia, at this King Abdullah University of Science and Technology. And he is very interested in that field, but I'm not sure if it is his work here in that case. Okay. Now we come to some funny pictures in the end. It's just remaining 32 slides, but it's very fast. So a lot of things are repetitive maybe. So, okay. Yeah, you know also the motivation. We don't want to have handcrafted models. And for instance, this is a visualization out of something what this is a French company for military training. They reconstructed some cities in Afghanistan, for instance, for military training, like with City Engine. Thales is the name of the company. It's a big enterprise. It's very interesting. They use it very, very fast. They adopted. Have been one of the early adopters of the technique because they use it really for training. So you can define cities from scratch. It's a new technique. You just start from the sketching and you set it up again. Sorry for the bad image quality. So that you already know. But there are some interesting results I wanted to show you. Actually, there was some things about cars. So GIS data, you can combine it. And you can encode some designs that have been created with commercial offices with City Engine. So you see we are stealing from each other's slides here. Some other planning examples. or that you can, how you can set up basic shape and distort and go around. So it's very, very basic functions inside city engines. So still two split strategies. We have facade surfaces, floor volumes. And where you can see we have different kind of possibilities to adding detail to the initial form. One is just to use textures, and the other one is really to have the hard-coded geometry here. Okay, multi-resolution assets. Maybe I should have had one. So sometimes if I use this service, I'm uploading pictures, and the result is sometimes strange. Sorry. I had a tinier computer screen that looked quite okay still. So this should be a flat roof, maybe you can imagine. So, oh, this is like hipped roof, what you can do. And now is more interesting part for you. So the idea is, oh, it looks really so bad, I don't know. Okay. So the idea is really that you have City Engine like as a formatting machine, where you get all the different kind of inputs, like shape files from GIS, DXF, OSM, OpenStreetMap data, OBJ, or FBX is the same, and images. And then you get as well, as an input, you have all the rules applied, and you get higher resolution, better resolution, or different modes of resolution models outside that you can give to different kind of technologies later on to use it for animation or for rendering, for instance. And this whole system can be used as well to let it run headless and to use a script generator that can optimize the code and as well regenerate the scenes and so on. So, So bad resolution, yeah. Game development is used to give you some insights more on that. You have here, for instance, City Engine. You have your scene. You can use Collada, put it out. You have it then in Unity. Do you know Unity already? You should Google it. You can just download it, and you really can try to connect 3D models, and you have a live playing 3D environment. For free, actually, there's a community edition. Then you have CryEngine. You know CryEngine? You're not into ego shooters, huh? So most of the ego shooters more or less rely on CryEngine. I guess so. I'm not as well so much into that, but yeah. Or Unreal Engine, maybe this is known. And it's very easy to make a connection between that. And oh shit. Okay, this should be a city, and this should be the little parts of the city that are just composed into the city. But unfortunately, JPEG compression was not so good. Sorry. Maybe next time I give you better images. Oh yes, I have to. Okay. As the idea, basically, what I wanted to show is that you have a lot of assets that you can import. It can be code snippets, can be 3D geometries that you have, and you combine it with your code, and you just place it and put it here, and okay. But unfortunately, there's not much to see. This example, I guess you know already. Oh, what is it for Genesis one? Image compression, really bad. Looked on the internet yesterday, quite fine. Yeah, and then you, of course, you can do all this analysis things that I just mentioned already. Media. Okay. So that was it. It was a bit long, but I guess it was very important to get you an overall wash-up about the techniques that are available for all the kind of modeling purposes that are all based on procedural modeling. And maybe I guess you will see some of the things in the future as well in the software world. It's just prototypes right now, but I think there will be some very interesting things come up, not just from City Engine, but from others as well. Okay, thank you very much. Yes, do you have a question?
small one. You mentioned the JPEG-based map generation, and as we had one tutorial, there was a JPEG with where the roofs were somehow encoded into a JPEG with only 2 colors.
Ah, okay.
And out of this map you could extract the roofs files very exactly, or the roof shapes.
Ah, yeah.
Is it easily possible to do those JPEGs by oneself?
Yes, it depends on your image data. For instance, I tried this one. This example, what you're referring to is if you have a city where you have like red-colored roofs for non-flat roofs, for hipped roofs, then you can use just a filter for this kind of color information in Photoshop, for instance. You just limit the color space to this colors of set roofs. Then you have this black and white maps, which is white may be true for having a hip roof, and black is just flat roof or something else. But for Zurich, for instance, we have a lot of dark shaded roof tiles for the hipped roof, so it's actually almost impossible to create those maps. If you have some more information, maybe from a GIS, then you can just directly put it from the GIS into the model. This would be another solution. But this was a very nice example to see that, yeah, but you made the tutorial. Great, thank you.
Yeah, but the program even calculated the angle of the roof somehow in comparison to the color. How did it work?
No, this is just by accident, I guess. It just looked right. But I wouldn't go so far that there was some further meaning. There's no much magic, but sometimes just luck. Yeah. Any other questions? No, not so far? Great, okay.